Welcome back to Talk Tensors. I'm excited for this deep dive because we're going to be tackling a paper that's really pushing the boundaries with machine learning and complex systems.
Yeah.
It's called Federated Granger Causality Learning for Interdependent Clients with State Space Representation.
Yeah.
And just from the title, you can tell we're in for a wild ride.
Definitely a mouthful.
Yeah. Okay.
But yeah, this paper is a head turner for sure.
So before we get into all the details, can you just give us like a high-level overview? What is this paper about and why should our listeners even care?
So this paper is all about trying to understand how different parts of a complex system, like a network of manufacturing plants or a power grid, influence each other over time.
Okay.
So think about like a single failure in one part of the system that can cascade and cause disruptions elsewhere.
Right, like a domino effect.
Exactly. And analyzing these types of systems is really challenging, especially with the massive amounts of data involved.
And that's where this paper's approach is really interesting, right?
Yeah, it combines two powerful concepts, Granger causality and federated learning.
Okay.
So Granger causality is a way of identifying potential cause and effect relationships between different time series data. And then federated learning allows multiple clients, like those individual plants, to collaboratively learn without sharing the raw data.
Oh, so it's like each plant is contributing to a shared understanding of the system, but keeping its own data private.
Exactly. That's a great way to put it.
Okay.
And that's huge for industries where data privacy is a major concern, like healthcare or finance.
Now, I remember from like my machine learning 101 class that traditional Granger causality analysis requires all the data in one spot.
Yeah.
But this paper is proposing something different, right?
Absolutely, they are.
Yeah.
They're using a federated learning framework, meaning each client, like a manufacturing plant, keeps its data locally and only shares model updates with a central server.
Gotcha.
And then that server uses those updates to estimate the overall causal structure of the system without ever seeing the raw data.
That's really clever. It's like having a team of detectives, each working on their own piece of the puzzle, and they're able to solve the whole thing without ever revealing all their clues.
I like that analogy.
Okay, so before we dive into how they did this, let's talk about the history of Granger causality.
Sure.
Can you give us a quick crash course on where this concept came from and how it's evolved over time?
Okay, so the concept of Granger causality was introduced by the British econometrician Clive Granger back in 1969.
So.
He basically proposed that if knowing the past of one time series helps you predict the future of another time series, then there might be a causal link between them.
Oh.
And this idea was groundbreaking at the time. It actually won him the Nobel Prize in economics in 2003.
Wow, a Nobel Prize. That's pretty impressive.
Yeah.
So how is Granger causality used in practice?
So let's say you're trying to understand the relationship between advertising spending and sales.
Oh.
And you have data on both of these variables over time. If you find that knowing the past levels of advertising spending helps you predict future sales more accurately than just using past sales data alone, then you could say that advertising spending Granger causes sales.
That makes sense. So it's like saying that the advertising is actually influencing the sales, not just randomly correlating with them?
Exactly.
Okay.
Now, over the years, Granger causality has been applied to a wide range of fields, from economics and finance to neuroscience and climate science.
Wow.
Yeah, it's a powerful tool for understanding complex systems.
But it has its limitations.
But it does have its limitations.
Yeah, I'm guessing data privacy is one.
That's a big one.
Yeah.
Especially in today's world where data is increasingly distributed and sensitive.
Right.
And that's precisely what this paper is trying to address by combining Granger causality with federated learning.
So they're taking this, well-established concept and giving it a modern twist to make it applicable in situations where traditional methods just wouldn't work.
Exactly. It's a great example of how researchers are constantly pushing the boundaries of machine learning to tackle real-world challenges. So we've established that this paper is kind of merging Granger causality with federated learning.
Right.
So let's actually look under the hood and see how they made it work.
Yeah, please. The concept is fascinating, but I'm curious about the nuts and bolts.
Okay, so remember how we talked about each client, like a manufacturing plant, having its own local model?
Yeah.
Well, the key to this framework is how they augment those models.
Augmented models, what does that mean?
Right. It's not just a plain vanilla model just sitting there. They've added a special component to it that specifically looks for influences from other clients.
So it's like giving each plant a little antenna that can pick up signals from its neighbors.
That's a great analogy. And that antenna is actually a machine learning function.
Okay.
They used a linear regression in this case, and it's trained using only the client's local data.
Wait, so how does it learn about the other clients if it's only using local data?
That's where the magic of federated learning comes in.
Okay.
The parameters of this augmented component are updated based on feedback from the central server,
Okay.
and this feedback doesn't contain the raw data from other clients,
Right.
but rather like aggregated information about the overall system dynamics.
Uh-huh. So the server acts as like a conductor,
Yes,
orchestrating the learning process and giving each client just a glimpse of the bigger picture.
exactly. It's like giving each plant a summary report saying, hey, based on what everyone else is doing, it seems like you might be influencing them in this way.
Gotcha.
And each plant refines its model based on this feedback.
It's a continuous feedback loop
Right.
between the clients and the server, allowing them to iteratively kind of refine their understanding of these causal relationships without sharing their private data.
It really is.
Pretty ingenious.
It is. But making this whole system work is not a walk in the park. There are definitely some challenges.
Like what?
Well, one is the issue of convergence.
Convergent.
So remember, each client is essentially learning independently.
Right.
So there's a risk that their models might diverge, meaning they start heading in different directions or get stuck in some suboptimal solutions.
Oh, so it's like herding cats, getting all these independent learners to agree on the same answer.
Haha. Yeah, that's one way to put it. So to tackle this, the authors actually conducted like a really rigorous theoretical analysis
Okay.
to determine the conditions under which this framework is guaranteed to converge to a reliable solution.
Interesting.
And it involves carefully tuning the learning rates and communication protocols.
So it's not just plug and play.
Yeah,
It requires some tweaking and fine-tuning to make sure everything's working together.
precisely. There's always that trade-off between achieving a good solution quickly and then maintaining data privacy.
Speaking of privacy, did they address how they prevent sensitive information from leaking out during this process?
Yeah, so they incorporated differential privacy analysis into their framework, meaning they add like carefully calibrated noise to the information shared between the clients and the server.
Oh, so it's like adding a bit of static to the signal, making it harder for anyone to reverse engineer the original data.
Exactly. It's like a balancing act
Okay.
between safeguarding privacy and preserving the accuracy of the learning process.
That makes sense.
It's a big challenge in the field of privacy-preserving machine learning.
They also mentioned scalability.
Yeah.
How well does it handle systems with a large number of clients and tons of data?
That's an area where further research is needed.
Okay.
Their current experiments were on a smaller scale, involving only a handful of clients.
Gotcha.
But how this would actually scale to systems with hundreds or thousands of interconnected components,
Right.
that's an open question.
Okay, so promising start, but more work to be done before we see this on a massive scale.
Yeah, definitely. And there are other limitations too.
Okay, like what?
For example, they assume that the relationships between clients are linear. But in a lot of real-world systems, those interactions are way more complex and nonlinear.
So they simplified things a bit.
Right, exactly.
Okay.
But this is like groundbreaking research, remember?
Yeah.
They're laying the groundwork for a whole new way of thinking about these systems.
This brings up a question. Where do you see this research heading in the future?
So one promising avenue is extending it to handle those nonlinear relationships.
Okay.
We might see more sophisticated machine learning models like deep neural networks integrated into the framework.
That would make it more complex,
Yeah,
but potentially much more accurate.
exactly.
Okay.
Another really exciting direction is using this for decision making, not just analysis.
Interesting.
Like imagine using this causal knowledge to actually optimize how a complex system operates in real time.
Maybe like having a decentralized brain continuously adapting and optimizing the system.
Right. But that opens up a whole new can of worms like stability, robustness, and ethical considerations.
Yeah.
It's an incredibly exciting area for future exploration.
So before we move on to our novel notions segment, do they talk about any specific details about their experimental results or the types of data they used?
They did. They actually tested their framework on 2 real-world data sets.
Oh, cool. Which ones?
So the first was from a steam turbine power and pumped storage hydropower generation system.
Okay.
They were able to capture the causal relationships between various components like the turbine speed, power output, and reservoir levels.
So it works in an actual energy system.
Yeah.
That's cool.
And then the second data set was from a water treatment facility.
Okay.
And they successfully identified how different treatment stages influenced each other, like the relationship between chemical dosage and water quality parameters.
So this shows their approach can be applied to lots of different areas, not just industrial settings.
Exactly. It highlights the potential of this framework to impact a bunch of fields where understanding and managing these complex, interdependent systems is crucial.
This is all really fascinating, and I'm sure our listeners are eager to hear what novel notions this paper has sparked for us. So shall we jump into that now? Okay, so it's time for Novel Notions, that part of the show where we let our imaginations run wild and explore potential extensions of the research.
Right, put on our speculative hats.
Exactly. So we've seen how this federated approach can uncover hidden causal relationships in complex systems while still respecting data privacy.
Uh-huh.
But what if we took this a step further?
Okay.
What if, instead of just passively observing these relationships, we actually use them to actively influence the system? Like, could we shift from analysis to control?
So you're talking about using this framework to optimize the system's behavior.
Exactly. Imagine each client in the network, instead of simply observing,
Okay.
is now actively trying to optimize its own performance
Yeah.
while also considering the impact on the others.
Like a network of intelligent agents
Yes.
working together towards a common goal.
And just like in a game, we need some sort of reward system to guide these agents, encouraging them to both optimize individually, but also cooperate globally.
So this sounds like we're venturing into multi-agent reinforcement learning,
Yeah.
where each client becomes an agent learning to make optimal decisions in this dynamic, interconnected environment.
Right. But with a twist.
Oh.
In traditional multi-agent systems, agents often have full or partial observability of the entire environment.
Right.
But in this case, we want to maintain those privacy constraints of the federated learning framework.
Ah, I see. So each agent would have to make decisions based on its own local data
Yes.
and the limited information it gets from that central server
Right.
without having a complete view of the system.
Exactly. And the central server, in turn, wouldn't have access to the raw data either.
Right.
It would have to rely on these aggregated signals from the clients to somehow coordinate their actions.
This raises some interesting questions.
Yeah, like what?
Like, how do you design a reward system that encourages both individual optimization and global cooperation?
Right.
And how do you prevent agents from falling into that tragedy of the commons scenario, where they prioritize their own gains at the expense of the whole system?
That's a great point. We'd need to strike a delicate balance there.
Yeah.
Perhaps we could borrow some ideas from mechanism design and game theory to create a system that aligns the individual incentives with the collective good.
Yeah. And we need to develop some really robust communication protocols to ensure that that limited information exchange between the agents and the server is sufficient for coordination.
This is starting to feel like a whole new research area. Federated multi-agent reinforcement learning, combining causal inference, federated learning, and multi-agent systems.
It's a compelling vision of a future where we can manage and optimize these complex systems
Right.
in a decentralized, privacy-preserving, and intelligent way.
Imagine the applications.
Oh, yeah.
Smart grids, traffic management systems,
Supply chains.
supply chains, yeah, even financial
The
markets.
possibilities are endless. Of course, there are some significant technical hurdles. Yeah.
But the potential benefits are so enticing, it's definitely worth exploring.
Well, that wraps up our deep dive into Federated Granger Causality and our foray into the exciting world of federated multi-agent reinforcement learning.
Yeah, and remember, this Novel Notion segment is purely for entertainment and brainstorming purposes.
Of course, we don't want anyone building a sentient AI power grid just yet.
Not yet.
But if anyone out there is working on something like this, we'd love to hear from you.
Please reach out.
And to all of our listeners, thank you for joining us on this intellectual adventure. And until next time, keep those tensors talking.